Hi everybody, welcome to another video in differential equation. I combine this section together. It's just a preliminary section. All of this will prepare for what we will do in section 9.5, 9.6. So the overview of this chapter. Now we will use matrices to solve system of equation. Right. First, if we have the linear homogeneous system of equation in the normal form, we'll have derivative on one side, and on the other side we have all the function. And if that is the case, we can put all the derivative into one matrix, or we can just say one column vector, and then the other side we have all the coefficients stacked into a matrix, and all the variables we put into the column of the variable. In that case, we have the matrix equation of that form, in vector form or matrix form. Notice that this x is different than that x. This is the boldface, which is a vector. This is boldfaced. Of course, for that too. The matrix, usually we just use a capital letter. That's just clear enough. But for the vector, that contain more than one components. So that will be boldface. So when we write like this, it is the vector. A vector is given in the columns, one column of a matrix. And when we say vector, usually we denote that to be a column vector. Right, so simple enough. We put all the derivative on one side and the function on the other side. And now, let's look at this example. We have x prime, y prime. If we put both of them in a matrix or a column vector, or a vector or a column, and we take derivative, right? Derivative to the top, derivative to the bottom, which is good. Derivative to the top entry, derivative to the bottom entry, which is good. Now we have this column for x, this column for y. The coefficients are 3, -5, 7, 2, and then we have the column of the variable. The first one is x, the second one is y. So it's simple as that. If we want to, we can if we let x be the matrix of x and y, then this is x, and this is derivative of x, and equal to the matrix A times x. So we write that in the matrix form. Okay, that's the matrix form. Right, so simple enough. So pretty much we just align them. If we have x1, x2, x3 prime, we can put all of them inside a vector or the column, matrix of one column. And then on the other side, okay, that way. Let's just realign them first. x1 prime, x2 prime, x3 prime. Now, we have x1, x2, x3 on the left hand side. So on the right hand side, we should have x1, x2, and x3 as well. If we don't have that, just hit a space. So psi of t x2, because there's no x1 here, and 5e to the t x3, right? You have 7x1, no x2. So we have to align them so that all the x1 in this column, x2 and x3, and there's no x2 or x3, right? So that's what we have. If we want to, we can say it is 0x1, 0x2, 0x1, and 0x3. Of course, we can put in the 0 where there's missing entry in that column. And once we have everything aligned, we just write all the coefficients. 0 for x1 sine t, for x2 5e to the t, for x3 7x1 no x2 negative 4 cosine of t, 0 x1 x2, because we don't write x2, right? We just write the coefficient. And then 0. The x1, x2, x3 will be in this column. And then, of course, the other side we have x1, x2, x3, but with the derivative. So, yeah, we can write that in the matrix equation. Simple enough. Just make sure that we have on the left hand side how many variables we have. On the right hand side we have the same variable. The left hand side we have the derivative in columns. So we have x1, x2, and x3 corresponding. Right, that's what we have. Right. Now, so we have the system of equation. We turn the system of equation into a matrix form, which is good. Now, can we turn a higher order differential equation in the matrix form as well? What we see is that if we write y1 as y and y2 as derivative, right? So if we let y1 be y, y2 is the derivative, then we can rewrite this system y prime, y double prime, move this to the other side. That's what we have. Right? So keep that in the back pocket. Now if we let y1 equal to y, y2 equal to y prime, then if we take derivative, derivative of y1 is y, derivative of y1 is y prime, derivative of y2 is y double prime. Then we can rewrite the system y1, y2 prime equal to y prime, y double prime, then y2, and then double prime we saw for this earlier, and then we can write that in this column, and finally we can put that in this form, in the matrix form. Right, let's see how it works. We have a few examples here. Y double prime plus 5t y prime plus sine t of y equal to 0. First, solve for the highest degree, highest order of derivative. Y double prime equal to, move that to the other side, minus 5ty, and move the sine t to the other side. I forgot to do that, so that should be minus. Right, sine t to the other side, that should be minus. Now, if we let y1 equal to y, y2 equal to y prime, then derivative of y2 is y double prime, right? Derivative both sides, that's what we have. So we have derivative, which is y2, y double prime is y2 derivative equal to minus 5t minus sine t y, and then the y1 derivative is y derivative, which is y2. So we have this system of equation, and we turn into this matrix form. Yeah, here I have the minus. I forgot to write the minus on the top. Right, so the point here is we will take the highest order to solve for it, which is already in the right form, so we don't have to do anything here, which is good. If it is not, if it is equal to 0, we have to move so that we will solve for the highest order of derivative. So in that case, we're going to keep that. And then we keep the highest order by itself. The other, we just write using a variable. I could use x, or could use y, or could use anything. Let's use x. Right. So let x1. Now we have the second derivative, and the function on the right hand side, right? So if I let x1 be the function x2 derivative and x3 is equal to z double prime. Right. Now, let's just take the derivative of everything. x1, if we take the derivative, what do we have? Z prime, right? I just write this again, but in a column. Derivative, and then I write this, but with derivative. Right? And then I'm going to write that, but take derivative both sides. Simple enough, right? Now, the rest will be easy. What is z prime? That is z2, right? I mean x2. Z double prime, that is x3. Z triple prime is going to be that. So z double prime plus at z prime plus 7z. Now, if we write this in terms of x, z double prime x3 z prime x2 7z 7x1. Now with that, we can rewrite this in the matrix form. x1 prime equal to no x1, but there will be an x2. x2 prime, there is no x1, x2, but there is x3. And x3 prime, we have 7x1 e to the t x2 plus x3. Once we have that, we can write in the matrix form. x1, x2, x3 prime equal to the matrix no x1, there's 1 x2, no x3, no x1, no x2, there's 1 x3, 7x1 e to the t x2, and 1 x3. And then we just have a column of x1, x2, x3. Right, so we can write that in the matrix form nicely. So whether we have a system of equation or whether we have a linear higher order of differential equation, we can write that in the matrix form. Or we could have both. A system of higher order derivative, higher order differential equations. Right, same thing. Now what do we have? Just on the left hand side we have y prime, y double prime, and x prime. So in that case, what we need the variables for was everything with less than that. So if we write, we have y double prime on this side, and we have x prime on this side. So on the left hand side we have to have the order of derivative less than that. So the left hand side we're going to have y and y prime, and on the less degree than x prime is x. So we going to need 3 variables for these 3. Right? So we have x. So let's use z, something else, or we could x. Doesn't matter. I would just use. Don't want to use t though. let's use z, right? z1, we're going to have 1 for x. We're going to have every variable that have less order than what we have on the left hand side. The left hand side we have the variable to the highest order of derivative. On the right hand side is everything less than that. So we're going to have x, and we're going to have y, and we're going to have y prime. Right, so that's all we need. Then we can write in terms of y double prime and x prime. Right, now next we take derivative on both sides and put that in the system equation. z1 prime is equal to x prime. Alright, z2 prime is equal to y prime. Alright, z3 prime is equal to y double prime. Right, so we write like that. Everything with less order than those two. And then we take derivative both sides, put that in the system of equation. Now, what we are given, x prime is going to be 2y prime minus 5 e to the t x. That's what given. Z prime, z2 prime of y prime. What is y prime? Oh, z3. And y double prime is this. Right. Now since the left hand side have only z, we have to write everything on the right hand side in terms of z. 2 y prime is z3 minus 5 e to the t. X is z1. z3, right? 3x, 3z1, y, z2, plus sine t, y prime is z3, right? And then we just realign them. z1 prime, z2 prime, z3 prime. Right, z1 and z3, no z2, so negative 5 e to the t, z1, no z2, but there will be 2 z3. Right, z2 prime, that's just z3. And then z3 prime, we have 3z1, a z2, and then sine t, z3. When we write like that, we can write as a system, as the matrix equation. x1, we can use x if we want to, but this problem we use z, z1, z2, z3, derivative equal to negative 5 e to the t, no z2, 2 z3, 0 z1, 0 z2, 1 z3, 3 z1, 1 z2, sine t, z3, and then we have z1, z2, z3 on the other side. So simple enough. So when we look at the system equation, move the highest order of derivative, keep that on the left hand side, and then on the right hand side we're going to have all the function and the derivative which order less than what we have on the left hand side, and so that's what we have. let's look at this example. What we have on the left hand side is y double prime and then x double prime. So what we need on the right hand side will be all the function and derivative of the order less than this, meaning y and y prime, y prime, and then x and x prime. So all the function and the derivative that has order less than what we have on the left hand side. Right, so in this case we're going to have x prime, y prime. So that's what we start with. We can do z or u or whatever it is. Let's just use x if we want to. Like x1 is x, x2 is derivative of x, and then we have y, so make that x3, and y prime is x4. Right? So first we need to know how many variables we need. So when we write like that, we know we need to have 4 of them. So x1, x2, x3, x4. That's what we have. And then the next step is we take derivative on both sides and put that in the system of equation. x1 prime is x prime, x2 prime, x double prime, x3 prime, y prime, x4 prime, y double prime. Simple enough, right? So determine how many we need and then just write out on x1, x2, x3, x4, and then take the derivative both sides, put in the row. Now x1 prime, x prime is x2. On the right hand side, I will not write x1 prime. The right hand side must be the function. There will be no derivative on the right hand side. So that's why x2 is x prime, which is good. X double prime is not here, but it's there. So it will be 3y and 6x prime. Just put that for now. X3 y prime is x4, and y double prime is going to be 5x plus 4y prime. Right. Now, remember the right hand side has no derivative, but have to be in terms of x1, x2, x3, and x4. So what is 3y, 3x3 plus 6, x prime is x2. Right? 5x, x is x1. 4y prime, y prime is x4. Yeah, so this is easy to write. Take derivative, and on the right hand side, rewrite that in terms of all of the x1, x2, x3, and x4. And then with that we can put in the system of equation where we align the variable. So it's easy to put in the matrix. There's only x2. Right, x2 prime, no x1, but this is 6x2 and 3x3. X3 prime, there's nothing but x4, x4 prime, 5x1 and 4x4. Right, so we have a matrix x1, x2, x3, x4. That's the vector derivative, and now we put in the matrix no x1, 1x2, 0x3, 0x4, 0x1, 6x2, 3x3, 0x4, 0, 0, 0, 1, 5, 0, 0, and 4 times x1, x2, x3, x4. Right. So, as you see, we can turn a system of differential equation into a matrix form, a higher order differential equation into the matrix form, like what we did here. Or we can turn a differential equation or system of high order of differential equation into the matrix form. So pretty much we can put that in the matrix form. The key here is it has to be linear. If we have, let's say, y prime square, cannot put in the matrix form if we have a square. Right. Now, what do we do when we have the matrix? So before we go any further, we have to know how to do some basic operation on matrix. So for example, if the matrix A is that, B is that, and C is that, let's do A plus B, I mean 2A plus B. Uh, 2A, it's going to be 2 times the matrix A, 1, 3, negative 1, and 4, 3, and 5. And then plus the matrix B, 0, 3, negative 3, 0, 5, and 4. So when we multiply a number to the matrix, we multiply the number to every entry of the matrix. 2 times 1 is 2, 2 times 3 is 6, 2 times negative 1, 2 times 4, 2 times 3, 2 times 5. And then add the matrix. When we add them, just add the corresponding entry. 2 plus 0, 6 plus 3, negative 2 minus 3, 8, 6 and 5, 10 and 4. Right. So that is where we add. Of course, subtract will be the same thing, or multiply the numbers to it. Now, how we multiply matrices? Before we multiply, if I add matrix A and matrix C, there's no corresponding to add. So in order to add them, we have to have the corresponding. Right? Now, how do we multiply? 1, 3, negative 1, 4, 3, and 5. That is A. Matrix C, 2, 4, negative 1, and 4. Now this is in course algebra. Or if you have been taking linear algebra, that will help a lot. If not, that's fine. So when we multiply the matrix before we do anything, just look at this is a matrix that has 1, 2, 3 rows. Three rows and 2 columns. This one has 2 rows and 2 columns. So when we multiply the matrix, first we look at the dimension. So 3 times 3 by 2 and 2 by 2. The middle number must match. If the middle number do not match, it cannot be multiplied. So we have the middle dimension match. And then we're going to have a 3 by 2 as the result. So the result is going to be a 3 by 2 matrix, the outside number. So we're going to have a 3 by 2 as the result. So just write the 3 by 2. Right. Then the rest is easy. This entry is on the first row. first row, first column. So the rows from the first matrix, the column come from the second matrix. So 1 times 2 plus 3 times negative 1. What's that? So we have 1 times 3 plus 2 times minus 1. So 3 minus 1 is going to be 1. Right. Next, this one is on the first row, second column. So we're going to use the first row and the second column. Right. 1 times 4 plus 3 times 4. 1 times 4 is 4, 3 times 4 is 12. That gives us 16. And then next, this on the second row, first column. So second row, first column, negative 1 times 2, negative 2, 4 times negative 1, negative 6. So of course when we multiply the row, there are 2 of them each. So negative 4, 1 times 4, and 4 times 4. So that's why the middle number mismatch. So that will be the corresponding. One go across, one go down. They have to be the same number of elements. Negative 1 times 4 is negative 4. 4 times 4 is 16. That gives us 12. And finally, this one on the last row, third row, first column, third row, first column. 3 times 2 is 6, minus 5 is 1. 3 times 4 is 12. 5 times 4, 20, 32. Right. So that's what we do by hand. Now if we use the calculator, the matrix is here, that button, but we have to hit second, the matrix. When we do that, we have 3 tabs. The first one is name, the second one is math, and edit. In the first tab, names, that's where we recall the matrix. For example, if that we have the matrix A, right? Now, and then if we want to input the matrix, so to recall the matrix, the first tab, this tab is to input the matrix. So we give here to input the matrix. This matrix A is 2 rows, 3 columns. So we have 3 rows, 2 columns. The entry 1, enter, 3, enter, negative 1, enter, 4, 3, and 5. Right, once we're done, second, quick. Go back to the matrix. Now under A, we have the 3 by 2. Let's go to enter matrix B. So go to edit to input the matrix. Do not hit this again, so I have to go down. Now we edit the matrix B, which is also 3 by 2. So I have 0, 3, negative 3. By the way, if you use negative, use this negative. Don't use that subtract sign. Negative is here. And then 0. And then 5 and 4. Which is good. Once we're done, second mode. Now go back to the matrix. Second matrix. Go to edit. This time go to matrix C. And this is the 2 by 2 matrix. 2 and 4 and negative 1 and 4. When we're done, second mode. Now and when we go to matrix, we have all 3 matrices stored into the calculator. Now if we want to do the math, like 2A plus B, is simple enough. 2, second matrix. When the names is highlighted, hit enter, we will recall it. So 2A plus second matrix B. And so we have 2, 9, negative 5. So that's what we have. And then because how about A times the matrix C, under names, go down to C, and recone it. We have okay. I wrote this wrong. Okay, let's do that again. 1 times 2, the first with the first, the second with the second, plus 3 times -1, sorry. Right, so 1 times 2 and 3 times -1. You go across and going down simultaneously. Right, so we think we check. -1, 16, -6, 12, 132. So that's good. Right. How about C times B? So let's use a calculator. Second matrix. We have the matrix C times the matrix B. Right. Dimension mismatch. Right. If we write it out, matrix C 2, 4, -1, and 4, and matrix B 0, 3, -3, 0, 5, and 4. This is a 2 by 2, and this is a 3 by 2. The inner numbers do not match, so we cannot multiply. So there is a mismatch here. So the product is undefined. Right? So, of course, if we do this, when we take a row, multiply by a column, won't be able to do that because there are only 2 entries in the row, but there are 3 in the column. So cannot multiply. On the previous one, a row has 2, a column has 2. So 1 times 2 plus 3 minus 1. So that's good. Or 1 times 4 plus 3. 1 times 4 plus 3 times 4. Yeah. So that's why we have to check the inner dimension. So that's the corresponding. So we can multiply. Right. Next, inverse of a 2 by 2 matrix. We only do inverse of 2 by 2 matrix here. We won't do inverse of 3 by 3 or higher because that takes a lot of work. So inverse of a 2 by 2 matrix is given by this. First of all, the ADBC, A times D minus B times C is the determinant of 8. So I will say determinant of A is equal to AD minus BC. This. And what we do in terms of a 2 by 2 matrix, this 2 entry will interchange the places. So we change the places of those 2, and then we change the size of the other 2. Right. So let's find the inverse of A. So if that is A, then A inverse equal to 1 over the determinant 1 times 5 minus 4 times -2, and then in terms of the matrix, swap the places of these 2 and change the sign of the other 2. And then 5 and 8, 13. And then 5, -4, 2, and 1. We can just multiply the 1 over 13 into that. So give us 5 over 13, -4 over 13, 2 over 13, and 1 over 13. So 2 by 2 matrix. By the way, if we want the inverse of the matrix, we can just enter the matrix in the calculator and then hit the inverse. and we the inverse of matrix, we only define the inverse of a square matrix, right? For example, we have a matrix C is a 2 by 2, so if we do that and hit the inverse button, that gives us the inverse. We can convert to fraction there, right? Now if you want to find the inverse of this, store in the calculator and do the inverse. Now if your calculator can do everything on the home screen, the way we check this is hit second and the plus sign, second the plus sign, about, hit enter. It will tell you what operation system you have. If you're using the TI-84 plus, it should be 2.55. In that case, that we can do a lot of calculation with that. If it is the case, hit mode and go down and make sure that it is in the math print, not the classic print. Go to math print. That will be better. Right, now when we're done, just second mode to quick. If that is the case, we can just enter the matrix in the home screen. Hit alpha and zoom. Bottom menu pop up the matrix. This one is a 2 by 2, so 2 row, 2 column. And click OK. Important things here is when we enter the numbers in this form, do not hit the enter key until we're done. Instead, hit the arrow. Go to the next entry. Go to the next entry. And the next entry. And then to the highest. Inverse. Can we change the fraction? 5 and 13, negative 4, 13. Yeah. So of course we can just use the calculator. The bad thing is it doesn't work if it has the variable in it. But the formula here still works. Right. So B inverse equal to 1 over determinant. 1 over determinant. So sine times sine. Subtract cosine times cosine. Cosine times negative cosine. Interchange these two. And change the sign of the other two. This to cosine of x to negative cosine of x. Right. And we just have one sine square plus cosine square. And then we still have sine x, cosine x, negative cosine x, sine x. Yeah. So these two interchange, and the other two change the signs. Sine square plus cosine square is 1. 1 over 1 is still 1. So pretty much we just have that. Right. So simple enough, right? Now, same thing. Let's find the inverse of this 2 by 2 matrix. So we use the same formula, 1 over the determinant, and then change the signs of these two and change the place of the other two, right? So inverse of C, 1 over determinant, e to the x times e to the 3x. Minus, this has a negative, so minus a negative. E to the 3x. And then these two change the places. The other two change the sign. Right. E to 3x, e to x. Right. Next. E to the x times e to 3x is e to the 4x. Minus a negative, that's a plus e to the 4x. And I just copy the others. Right. Multiply that give us 1 over 2. I mean combine them 2 e to the 4x. E to the 3x. Negative e to the 3x. E to the x. E to the x. Now we multiply that inside e to 3x, e to the 4x. We will still have 1/2. E to the 3x over e to the 4x. 3x minus 4x is e. And then multiply that in will be 1/2. E to the negative 3x over e to the 4x. Subtract the exponent negative 3x, negative 4x, negative 7x. Then 1/2 e to the x over e to the 4x. That e to the negative. Subtract x to 4x. And 1/2 e to negative 3x. So that's what we have, 2 by 2. And when we have the matrix equation ax equal to b, do sum for x, we can multiply the inverse on both sides, and we end up with a inverse b. We revisit this later in section 9.7, I think. Next, we will have the Gauss-Jordan elimination. By the way, if you take in linear algebra, this by itself required a lot of work. I mean, if we do it by hand, that could probably take about 5 minutes, 5-10 minutes. But to explain the concept, it could take hours. So instead, we use the calculator. So I'm going to put this in the matrix and then just hit the button, reduce row echelon form instead of doing it by hand. So first, we put in the matrix, which is called the augmented matrix. 5, 8, negative 1. I will draw the vertical line to indicate there's an equal sign there. 36 x, which is 1. So put all the coefficients in the matrix. Negative 2 and 7 and 18, 3, 1, 1, and 21. So we have those 5, 8, negative 1, 36, 1, negative 2, 7, 18, 3, 1, 1, 21. Right. And then after that, we just do reduce row echelon form. Yeah. Reduce row echelon form. Right. So on the matrix, second matrix, let's store this into a matrix D. So go to edit, go down to D. 3 rows, 4 columns, right? So 5a, negative 1, 36, 1, negative 2, 7, 18, 3, 1, 1, 21. Once we're done, second mode to quick. Now we will go to second matrix. To go to the REF, we go to math and go down to way down to option B on my calculator or whatever it is on the RREF. Right, and we hit second matrix. We apply that to the matrix D, and we should have the identity matrix on the left hand side. If we don't have it, then there will not be a unique solution. So notice this is called the identity matrix, where we have 1 on the diagonal and 0 everywhere else. So this is called the identity matrix. If we have the identity matrix on the left hand side, then the right hand side will be the solution, x, y, and z. We will use this a lot in this chapter. Right, same thing here. Put that in the matrix and then reduce row echelon form, then to have the solution. If we have the identity matrix, then there will be a solution. Right. So 5, 2, 1, -11, 2, -3, -1, 17, 7, -1, 0, and 12. Reduce row echelon form. Right. Notice I did say that if your calculator is using the newest operating system, then we'll just do everything on the home screen, which I will do now. Second matrix, go to math, reduce row echelon form, and I hit alpha zoom to go to matrix alpha and zoom. 3 rows, 4 columns. Okay. Enter the numbers 5. Don't hit enter until we're done. 2, 1, and this is the negative sign. 2, -3, -1, and 17. 7, -1, 0, and 12. Well, let's check one more time. Right, once we're done, just hit enter and we can change to fraction. Right. So in this case, notice that we don't have the identity matrix here. What we have is a row of 0 and 1 at the end. If we rewrite this from the system of equation, this should be 0x plus 0y plus 0z, right, for that row, but equal to 1, which is impossible. Right? If you have no x, no y, no z, how can we get 1 out of it? We cannot make something out of nothing. So in this case, this is no solution. So when we have a row like this, it is the no solution. It has a solution if we have the identity matrix 1 on the diagonal, everything else is 0. So if that is the case, if we have the identity matrix on the left hand side, there is our solution. But if we don't have the identity matrix, there will not be a unique solution. In this case, we have no solution because no x, no y, no z cannot get something else than 0. So that's no solution. Right. Now, we have this. Once again, I'm going to put that was correct. Yeah. 1x, 1y, 1z, 1x, -1, y, 2z, 2x, 0y, 3z. Yeah, that's why I go back and check and make sure that I put in the matrix correctly. And then we just do reduce row echelon form and see what do we have. Do we have the identity matrix or not? If we have identity matrix, there will be a solution. If not, then there might be no solution. Right. I put everything in the home screen though. 3 row, 4 column. Okay. 1, Next, 1, 1, 1, sorry, 7. 1, -1, 2, and 7. No x, 2x, no y, 3z equal to 14. Alright, so that's what we have. Can we have fraction? Yep. So we have 1, 0, 3/2 equal to 7. 0, 1, and -1/2. 0, 0, 0, 0, 0. Now, what we see here is we have the whole row 0 at the bottom, which is not bad. Because if we write 0x, 0y, 0z equal to 0. So this is true for all x, y, z, right? So when we see this, this is infinitely many solutions. Now, but infinitely many solution doesn't mean anything can be a solution. Infinitely many solution means there will be a lot of them, but not anything can be a solution. So in that case, we have to go back and look at the matrix on the left. Whenever we have the 1, let's go in the basic column. So this column is basic. This column is basic because they have the 1 on the diagonal. By the way, that's what echelon means. It's the steps. Echelon means step. So kind of in the step. So we have 1 here, 1 there. Whatever the column have 1, we're just going to leave that alone. This column is non-basic. So when we have a non-basic column, the column that doesn't have the 1 on the diagonal or the 1 on the steps, so this is non-basic. Or doesn't have the pivoting 1, or there's a lot of name for it, but I've just called that non-basic. We're going to let that variable to be arbitrary. So that corresponds to x, y, and z. So I would choose let z equal to t, and that is arbitrary. Right, keep that in the back pocket. Now the other two equations, can we rewrite this as 1x, no y, 3/2 z equal to 7, right? Which is good. Next, this column, no x, but y minus 1/2 z equal to 0. Right? Now, with that you can solve for x and solve for y in terms of z. From this, we have x equal to 7 minus 3/2 z. Y equal to 1/2 z. And z is equal to t. So we can have the solution as x equal to 7 minus 3/2 z, y equal to, we use t because z is equal to t, y equal to 1/2 t, and z is equal to t. So the solution will be in this form where t can be any real number. Right, so that's where we have 3 scenarios. If we have the identity matrix where we have 1 on the diagonal, 0 everywhere else, that is identity matrix, so we have a unique solution. If we have a row of zeros everywhere except from the last one is not 0, that is no solution. if we have the whole row of zeros, that is infinitely many solutions. Right, so those are the three scenarios that we have. Right. And next we just go over all of the theory. We'll revisit this a little more in the later section, but here it is. Alright, matrices and system of equation. If A is n by n matrix, the following are equivalent. A is singular, doesn't have inverse. Determinant of A is 0. By the way, this would be an m by m, so a square matrix. H of x equal to 0 has non-trivial solution, and the rows or the columns of A form a linear independent set. Was that a lot more theory? We study about that in the linear algebra. I'm just going to put that here. We rarely use this. Of course, we will use that in the next section, but when we need it, I will explain that again. But a little more theory, which we do not need all of it. Calculus of matrices. If we want to have the matrix, when we take derivative, we just take derivative of each entry. If we integrate each entry in the matrix, simple enough. And differentiation of the matrix function. Right? We have derivative times a constant times a function, constant times the matrix. Derivative of a sum is a sum derivative. Derivative of the product, this is the product rule, but in the matrix form. Like I said, we revisit this if we need it. Right. Now we go to section 9.4. It's just a theory, as you see in this section. I will not have any example in here, just the theory part of the chapter. So, a system of linear differential equation is said to be normal form if it is expressed as this form. Remember what we have earlier, we don't have f of t, right? If we have f of t is something other than 0, then we have the non-homogeneous system. Earlier, we only have the homogeneous system. Non-homogeneous is something like this. Let's say if we have this equation and have the plus 1 there, then it's no longer homogeneous. But of course, the easy way if we fix that is we're just going to add the matrix like this, and that is the part that makes it non-homogeneous. Right? So simple enough. If we have the term that does not depend on the variable in the column, that means it is non-homogeneous, and we're just going to add that at the end. And that is essentially what we have in this here. We just add the function at the end or not. Right. And then also the higher order, we can rewrite this as the system, as a system of the equation or the matrix form. That is exactly what we did here. System of equation, the high order equation turned into a matrix form. So that's why I said high order derivative, high order linear differential equation. We can turn that into the matrix form, and we can whatever g of t, we just have to add at the end. An example here. Right. Let's look at this example. Let's say if I have a function here, let's say 2, simple enough, right? That means I'm going to add 2 at the end here, only to the last one. So we only need to add to 0, 0, and 2. Yeah, if we have the numbers that does not depend on the variable, that's what we add only to the last row and the matrix in the last row. Like I said, when we need this in section 9.7, we will revisit, and so we will have that. Right, existence and uniqueness. If A of t, the matrix, and F of t is a vector, are continuous on an open interval containing the point t naught, then for any choice of initial condition, they have the unique solution. And representation of the solution, because what we have here is exactly like what we have before. Linear independence. It is linear dependent if this equal to 0 and or not all of them equal to 0. And that is a lot better. We use the wrong skin. The wrong skin, if we put in the matrix all of them will form a matrix phi determinant. If it is equal to 0, then it is not linearly independent. And we said the set of n of all of those is linearly independent if their wrong skin is never 0 on an interval I. So if the wrong skin is not equal to 0, that will be linearly independent. And if it is linearly independent, we can write the system, write this as the solution. And in that case, we just have the linear combination of the solution. So this is exactly like y equal to c1 y1 c2 y2. So this theorem will be the same, except this will be in the vector form. So we have the boldface for the vector form. That's the only thing different. And then of course, if we have a particular solution, we add to this. So pretty much what we have here is exactly the same as before, except that in this form we have in the vector form. That is all. Like I said, when we go back to this in the section 9.7, I think, then we'll revisit this. But the wrong skin not equal to 0, linearly independent. Right. So before I end section 9.4, just do one example real quick. What happens if we turn an equation that is not in it's not homogeneous? How we turn that into the matrix form? So we're going to write, let's say, right, in matrix form. Yeah, just want to do one example like this before I end the section. Right, simple enough. What we do is first keep the highest order, move everything to the other side. Negative 2y prime plus 3y plus sine t. Right. Now what we need is everything up to the function and derivative less than this. So we're going to need 3 of them. So we start with, let x1 be the function, x2 be the derivative, and we still need the second derivative because that up to x3. x3, because that had the third derivative, we have to have everything of order less than that, including the second derivative. Right. Then we can take the derivative of each of them. x1 prime, y prime, x2 prime, y double prime, and x3 prime, y triple prime. Right. Now we'll rewrite. The y third derivative is equal to this, so I have negative 2y1, negative 2y derivative 3y, and sine t. Right. Next, y prime. If we don't want to use the derivative, that is going to be x2. Y double prime, that x3. So if we put this in the matrix form, actually I'm just going to do that. There will be no x1, but there's x2. There's no x1, x2, but there's x3. And here we have y, which is x1. So we have 3y, which is 3x1. Minus 2y prime. Y prime is x2 minus 2x2. There's no x3, but there's sine t. Right, so put that in the matrix form, and so we have this. We give us the matrix, and the sine t doesn't have x1, x2, x3 will be in the second matrix. So put them all together. This is what we're going to have: x1, x2, x3, derivative, the matrix 0, 1, 0, 0, 0, 1, 3, negative 2, and 0, x1, x2, x3. The sine t by itself only apply to the last row, so we're going to have 0, 0, and sine t. So we write this non-homogeneous system into the matrix form. Right, I just want to do one example of this before we end the section. Right, anyway, so now what we learned here is that we can write a differential equation, a linear differential equation, into a matrix form, or the system of linear differential equation into a matrix form. And in the next section, we'll study what do we do with the equation in the matrix form. But I'm going to end the section here. As always, thank you for watching, and see you in another video in differential equations.